alpha carbon. That's why we call those alpha amino acids. So this is C alpha. We have a carboxyl group and a amino group. And we talk about different categories of amino acids. Do you still remember those?
Yeah. Polar, non-polar.
How many?
7.
7. Non-polar, aliphatic, aliphatic amino acid. And 5, polar and charged amino acid. 3, aromatic amino acid. And what are the 3? Tyrosine, tryptophan, phenylalanine.
Oh, yeah, the tryptophan.
Tyrosine, tryptophan,
That's called tire.
and phenylalanine. And what's the one letter code for this? F. F, Y, W, W. Remember what Y is W?
Because it's shaped like a W on the side.
And there's also a 3 positive charged amino acid. 3. Lysine, arginine, and histidine. Okay, what is the one letter code for lysine? Okay, this R, H. And then we have a 2 negative charged amino acids. What are the 2? GL, U, aspartic acid, ASP. Okay? What is the one letter code for this 2? This is an E, this, E. Okay. All right. So 75332. And altogether we have 20 standard amino acids. Then we talk about the pKa. And amino acids can be expressed as a deuterion with a positive charge and negative charge. Positive charge on the amino group, alpha amino group, and negative charge on the alpha carboxyl group. And what is the pKa for the COOH? Carboxyl group. Roughly. Okay. What about pKa for the amino group? 9. Okay. So at pH 1, what's the form of the carboxyl group? COOH. What about pH 5? COO minus. What about pH 8? COO minus. pH 13? COO minus. What about pH 1 for amino group, upper amino group? NH3 plus. Will be protonated. What about pH 5? Protonated. NH3 plus. What about pH 8? Yeah, this one. What about pH 10? Those proton from amino group. What about pH 13? This one. So this is positive 1. This is neutral. This is minus 1. For the amino group, it can exist in positive 1 or neutral. For the carboxyl group, depending on the pH, it exists in neutral or negative.
And at 9, it's half and half, right?
Yeah. But there is also a pKr. So the side chain also sometimes will also have a pKa value. For example, this aspartic acid D, right, has a side chain contains a carboxyl group. This one has a pKr equals to 3.9. So this pKr, this R chain, R group, is a COOH. And pKr 1, what is the charge for this R group? Neutral, this is protonated. What about pH 5? It will be minus, it will be deprotonated. So this becomes a -1. What about the pH 8? Minus, pH 13 will be minus. Okay? So at different pH, if you combine all the charges on the amino acids, you can calculate the overall net charge for that amino acid at a certain pH.
So just higher pH and pKa is deprotonated.
Yeah. The lower the pH, it gets protonated. The higher the pH, it gets deprotonated. In this table, you can see the value of the real value of the pKa1 for the carboxyl group and pKa2 for the amino group and the pKr. And using that information, you can decide the net charge for that amino acid. Okay, so here is another concept called isoelectric point. Isoelectric point. The term alkalides are molecules that contain both acidic and basic pKa values. For example, we're talking about the amino acid. So at different pH, it can be positive charge, neutral, or negative charge. The isoelectric point, abbreviated as a PI value, is the pH where the average charge is 0. The PI lies midway between the two pKa values that indicate the protonation and deprotonation of the electrically neutral form. This is PI. PI is the pH value. At that pH value, the overall charge of this amino acid is 0. It's neutral. Okay, that is called the PI. I'll give you the example of this glycine titration curve. The glycine, you add strong base to the glycine, you're going to see the titration curve like this. And there is a pK1, there's a pK2. And because it's a glycine, there's no side chain, there's no pKr. So we only have the pKa carboxylic group and pKa amino group. So this is the pKa1, which is about 2.34 for this amino acid. And pKa2 for the amino group is about 9.6. So you keep titrating, and and at one point, at this pH value, the overall charge, this species is dominant. The overall charge of this glycine is 0. And there is this equation, Pi equals to pKa1 plus pK2 divided by 2. So half of the pK1 plus pK2 divided by 2, that equals to the Pi value.
Does that only work for glycine?
It only works for glycine. So let's try to understand why this is the case. So when you see such a problem, you need to write down the amino acid. I will give you the structure of the amino acid. And you need to understand there's a dissociation of proton and dissociation of proton from the carboxyl group and dissociation of proton from the amino group. All right. So pH, we know. pH equals to pKa1 plus the, what is the,
A minus.
that will be,
It's going to
let's use
be
the A0 for the middle, for the neutral.
so it'll be
And A
8.
plus for the left,
So
and
8.
A minus for the species on the right. Okay, just to simplify this. So this will be pH equals to pKa1 plus log
A
A0.
naught over A.
A naught divided by
A minus.
A plus. We're talking about plus is the first.
The one on the left is A
One
plus.
on this equation.
That's A plus.
That's A plus. Okay, A plus is A0, all right? And we talk about using this pKa. And pH also equals to pKa2 plus
Log.
log,
Minus over in
what is A minus. We're talking about the second equilibrium. This part, this is A minus, this is A0. This equation, this is the conjugate phase, and this is the weak acid. For this one, this is the conjugate phase, this is the weak acid. And the follow the Heisenberg equation, right? If we add these two together, right, this will be 2 pH. We're talking about that pH. 2 pH equals to what? pKa1 plus pKa2 plus log what? This, 2 together will be this times this, right? It will be A0, A plus, A minus, and 0, right? Can cancel this one, right? Should be canceled. All right. So this will be expressed as a pH, 2 pH equals to pK1 plus pK2 plus this. We define the pH, at that pH, the overall charge is 0. We define that pH as a pi value. Okay? Now, at which pH? Pi value? At positive equals to negative charge. Positive charge equals to negative charge is neutral, right? So this can be 1,
Yeah.
right? So because the net charge is 0, that's why negative charge equals to positive charge, easy. Follow me?
Yeah.
So this will be 1. Log 1 equals to 0.
0.
And we define that as a pi value, that pH as a pi. All right, so 2 pi equals to pKa1 plus pKa2. So pi equals to pKa1 plus pKa2 divided by 2. All right? Understand? This is how we got this. And
If we're looking for the isoelectric point, shouldn't, that's the point where there's not any COOH and no NH3 plus, right?
average of the positive charge. This is zero ion. That potential amino group will be positive. However, the carboxyl will be negative. We add them together. This will be 0. That's why this A minus all the negative charge will equal to the positive charge. And we derive this. So Pi equals to half of the pKa1 plus pKa for glycine. Now if we have a amino acid that contains a R group, the R group has a pK value, so pKr, right? Then the titration curve will be different. The titration curve looks like this. It will first titrate, when we add the strong base, it will first titrate and pass the alpha carboxylic group. And then it will move on to go to the titrate, the COOH, the alpha, the side chain carboxylic group. And then it will go to the third one, that will be the alpha amino group with the higher pH, pKa. Okay?
Will the primary carboxylate group always be protein first?
Typically. So let's say because it has a pKa value very low, 2.12, roughly 2, we're talking about, right? That is extremely low. Okay, so now when we have this one protonated, this one neutral, right? At low pH, this is positive 1, right? And then this one this carboxyl, alpha carboxyl, will start to dissociate the proton. But this one still not yet to that pKa value, so this will be neutral. This is positive, and this is the neutral species. Then this one will start to deprotonate, right? This one, and we titrate to this point. This starts to deprotonate, and this will become -1. This become -1. This will become +1. So overall charge for at this stage is -1, and for this one will further dissociate, become neutral. It's be -1, and the net charge will be -2. Okay. If you see such a problem, you need to look at the equilibrium. Look around the 2 pK values around neutral charge. That means you need to write down all the equilibrium. All right? Then you identify, okay, at this point there is a neutral charge. And this will be, so the PI value should be in this range. Right? Between this pKa and this pKa. All right? Because this 2 pKa is too high, and our PI value will be in this range, this species will be ignored. We talked about that when we discussed the buffer problem. So now the PI equals to, so we'll just use this equilibrium to calculate the PI. PI equals to pKa1 plus the pKr divided by 2. So the principle is that you use the 2 pKa values around the neutral point, neutral species. Then you add them together, divided by 2. That is the PI value for this amino acid. You can do the same to derive this. This will be cancelled, right? So the negative charge and the positive charge of species will be equal at that point. PI equals to the pH. If I have a different amino acid, if I write it that way, the histidine will have a +2 and +1 and 0 and -1. Now you look at this equilibrium, and you identify that neutral species, neutral charge species, is between the pKr side group and the pK2, the alpha amino group. Then you add this 2 plus this 2 together, then divide by 2. That will be the PI value for that species, for the histidine. Okay? So the PI value equals to pKr for the histidine, the side chain pKr, plus the pK alpha amino group, and then divided by 2. 9.17 plus 6.0 divided by 2 equals to 7.59. So at pH 7.9, 559, it's neutral charge. The amino acid is neutral charge. So that is the PI value, isoelectric point of that amino acid.
What about amino acids that don't have like the same groups, like a cysteine? Like could that acid?
If that has a R group, then you use that R group. That means you can any species, any group that can dissociate a proton, you consider the pKr. Okay. Any questions on the PI value? If I gave you a amino acid, can you calculate the PI value?
When you say you give us a structure or name, will you give us a chart?
Yeah, I'll give you a chart.
Okay.
What about lysine? Let's talk about lysine. Lysine has a pKa1 2.18 and pK2 8.95, and the R group is 10.53. What is the PI value?
It's probably going to be between the 2 and the R.
I'll try to figure that out.
Okay. All right.
Just pick one and write it down.
Let's write it down. Why don't we write it down? Lysine has a CR alpha, COOH, I like to use the left part of the board. And it's like the parking garage always turn left.
That's hard.
Okay, lysine CR NH3 plus COOH and CH2 4 3
Yeah, cool.
and COOH. Okay, so this can dissociate the proton. Which one dissociate first? This one?
Yeah.
Okay. 3 CR plus COO minus CH2 4 COOH. This is the pK A1. And then it goes to NH3. What is pKr for this one? 8.95, right? CR plus COO minus CH2 or COO minus. Then pK two, CO minus, H2, 4, CO minus. What's the overall charge for this one? Minus 2?
Minus 1.
Minus 1?
0.
0?
Plus 1.
Positive 1.
Plus 1 plus
NH3 plus, sorry.
Minus, this is not a positive. 0. Positive 1, 0, minus 1, minus 2. Okay, so we need to consider which one? We should consider this,
Zero.
this part, right? Okay, because it's 0 neutral at this range. So we need to add up this plus this divided by 2.
Yeah.
It looks like the table is something wrong with the table. Okay, and pK ACOOH equals to what? So lysine 2.18, right?
Mm-hmm.
pK R equals to what?
8.95.
by 3.
Well, 10.96, yeah, correct. So 2.18 plus 10.53 divided by 2. What's the
6 minus 3.
6 point,
That's more than that. 6 minus half of 70, half of 82. 41.
I know what's going on here. So we're talking about lysine is a positive charge. We're talking about the aspartic acid.
Oh, that's why.
Let's do this one more time. We're using the aspartic acid instead of the lysine. NH3 plus. Okay. So this one will be NH3 plus. And then this one will be pKr equals to what? pKr. Then this one will dissociate NH3 plus will be NH2. Okay. So what's the charge for this one? This is positive 2, right?
Mm-hmm.
What about this one? That's positive 1. And this one? 0. And this? Minus 1. So we use this part. Alright? We add this pKr plus pKa divided by 2. pKa are amino acid, amino group divided by 2. So that is 8.95. 8.95 plus 10.53 divided by 2. 8.95 plus 10.53 divided by 2. So the answer in the table is correct. Got it? Yeah?
Was this supposed to be NH2?
Yeah, the R group plus
Yeah, this one NH2, NH2.
the bottom one
This
should
one
be,
NH3.
the R,
This one dissociate first. NH2.
the R group is higher PK.
This one, this alpha amino acid group, you see, the pKa is lower, even lower than the pKr. So the alpha amino group will first dissociate the proton, then this one. So you increase the pH. Next.
The one that has a low pKa will be
NH3 first. Form part.
Yes. Whenever you have a lower pKa, that group will dissociate the proton first, or change the charge.
So that means we ignore the pKa.
Yep. I'll give you the pKa, pKr, pKa1, pKa2. Okay. Sorry about this. I was using aspartic acid. All right. Let's go to. Do you understand this? The PI value?
Yeah. I'm confused why, so where it says pKr,
Yeah.
nothing changes in the R group on that reaction.
That's why you have this. This one is pK.
It should be PKA2 and then PKR.
Sorry. It's pKa alpha amino acid. pKr. Because this has a higher pK value. So this one will first dissociate the proton, and then this one will dissociate the proton.
Could you go back to the values of pKa for that one?
Hmm?
Could you go back to the pKa values for that one?
pKa
For
value
leucine,
for leucine.
or whichever one you said.
This is the lysine. Lysine value. This one?
Yeah, so
Okay.
which
This one?
which is
So
pKa?
pKa1 is 2.18, pKa2 is 8.95, and pKr is higher than pKa1. This is why this amino group dissociates the proton later than this alpha amino group. Got it? Good. I recommend that you go back home and find the table and use several examples to calculate the pKa value. Yep. Right, because as neutral species, neutral charge, that is where the pH should be. So this is far away from this pK value. If you do the Henderson-Hessenbach equation, you will know this, the ratio between this species and this one or that one is too low. So we can just ignore it. This doesn't exist. That's why we use this equation. We talk about the overall charge. And then you simplify the problem like the lysine, right? Then you use what we derived to get the PI value equals to half of this, using two Henderson-Hessenbach equation and add them together and then cancel the charge. Got it? Yeah.
Doesn't matter which NH3 gonna lose first, like the photon?
It will matter. Now it matters. Yeah.
So because of the closest to
Yeah.
the
Given a pK value, so the lower the pK value, the earlier it will deprotonate.
The lower acidity.
Okay. Yeah. All right, stereochemistry of amino acid. Amino acid has a certain stereochemistry, and in the natural amino acid, they are in L configuration. L configuration. So all the amino acids incorporated in proteins, in natural proteins, they are in L configuration. So you have a L adenine, L glycine, glycine doesn't have a zero. L adenine, L lysine, all these groups. So when we have the amino acids, you have multiple amino acids, you can come together through a condensation reaction. Water will dissociate the two amino acids together. Then we will condense into a peptide. So you have a C-alpha carboxylic group on the right, an amino group on the left, and another amino acid is R, another side group R2, amino group, and carboxyl group. When these two come together, will dissociate a constant condensation reaction, dissociate water. Then this will form the carboxyl group will connect with the amino group and form an amide bond or peptide bond. Peptide bond is also called amide bond. Okay, CO and H. And in chapter 4, we'll talk about the structure of this amide bond type. Right. And then you have a positive charged amino group and the negative charged carboxyl group at pH 7. Right. This will be the N terminal, this will be the C terminal. And another amino group, another one come here and further condense the water so you can make this chain, polypeptide chain continuous.
So it adds the C terminal?
Yeah, the C terminus or N terminus. If you have another one, the COOH will react with the NH3. All right, this is an example of a polypeptide containing 1, 2, 3, 4, 5 amino acid residues. So you start with serine. This is side group of serine. And this is the glycine. This is tyrosine. This is alanine. This is leucine. All right. So when you have all the peptide bonds formed, 1, 2, 3, 4 peptide bonds, you have the alpha amino group, amino terminal, N terminal. You have a C terminal, carboxyl C terminal. In between, you have side chains. Right. Now, if the side chain can contain charge with the pKr, you can also calculate the overall net charge of the peptide at different pH. Okay. For example, if we have 2 amino acids, a diet peptide, if the first one is a lysine and the second one is a aspartic acid, and what is the pH? What is the net charge at pH 1? 0. This will be positive charge. This will be neutral, right? This will be neutral. What about this one? Lysine NH3 plus. At pH 1 will be positive. What about this one?
What is it?
What about this one? Okay, I gave you the aspartic acid, the pKa equals to 3. This will be neutral. Neutral, neutral, positive, positive. It will be positive 2. All right. Then we talk about pH 7 and pH 9 to calculate this.
Does being joined change the pKa?
We'll give you that. Roughly, you will speak to that pKa. Understand this point? You guys are smart.
Right.
All right. So this is another example with the 4 amino acids: alanine, glutamic acid, glycine, and lysine. Right. This one can carry a negative charge. This can carry a positive charge. So at pH 9, at pH 13. What is the net charge for this peptide? pH 13. What's the charge for this one? pH 13 for the N-terminal. Neutral. Yeah, this is associated, right? Remember, this one has a pKa about 9, right? So this will be neutral. What about this one? -1. Right? This is already dissociated proton. What about this one? Neutral. Okay. I gave you which is about 10.53, right? So it will be neutral. And this one? Negative. So it's negative, negative, neutral, neutral. What is the overall net charge for this?